Back at it. Alright, so I was here earlier and then everything crashed. I cried. Now I'm back. Hi. Oh, my shit's it's really loud. Hold on. Okay, so what are we doing now? Well, I was gonna do an open courseware class on statistics, right? And I don't think I'm quite there yet. I'm not quite there yet. So we're gonna explore this. This is probably also more than my current level of mathematical literacy, but we're gonna try it anyway. We have Introduction to Probability, so ready to learn some gambling. JK. All right. So, but there were some other probability videos or a probability course that the other course. Oh, hey, come here. Stop it. It's my child. Say hi. Oh, okay, go over there. Okay. Stop it. It's almost her dinner time, so she's getting annoying. I love you. But no, please stop it. Go bother your mother. All right, so the other course didn't have lecture videos. I feel like watching some lecture videos, so that's what we're gonna do. We're gonna watch. Hey, come here. Are you having fun? Okay, that's fine. All right, so we're gonna watch some of these videos and learn some probability. I'm into it. Let's do this. All right, so we got probability models and axioms. We've got lecture 1, 2, blah 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 blah. Okay, there's a whole bunch of stuff. So let's sit back, relax, and watch and learn some probability. Maybe I can pull up the PDF slides. And away we go.
Welcome to the first lecture.
Hold on. The sound isn't coming. Oh, I know why the sound isn't coming through. Okay, now let's try.
Of this class.
It's still not coming through.
You may be used to have.
Here, I'm gonna try this. Goodness gracious. Stop it. Stop it. Oh my goodness. My children. Okay. Love this. All right. This should work.
This one will be different. We will dive into the heart of the subject right away.
It should work, and yet it's not working.
In fact, today we will accomplish a lot. By the end of this lecture, you will know about all of the elements of a probabilistic model. A probabilistic model is a quantitative description of a situation, a phenomenon, or an experiment whose outcome is uncertain. Putting together such a model involves two key steps. First, we need to describe the possible outcomes of the experiment. This is done by specifying a so-called sample space. And then we specify a probability law which assigns probabilities to outcomes or to collections of outcomes. The probability law tells us, for example, whether one outcome is much more likely than some other outcome. Probabilities have to satisfy certain basic properties in order to be meaningful. These are the axioms of probability theory. For example, probabilities cannot be negative. Interestingly, there will be very few axioms, but they are powerful, and we will see that they have lots of consequences. We will see that they imply many other properties that were not part of the axioms. We will then go through a couple of very simple examples involving models with either discrete or continuous outcomes. As you will be seeing many times in this class, discrete models are conceptually much easier. Continuous models involve some more sophisticated concepts, and we will point out some of the subtle issues that arise. And finally, we will talk a little bit about the big picture, about the role of probability theory and its relation with the real world.
Okay. They don't really make this easy, huh?
Putting together a probabilistic model, that is, a model of a random
Interesting. Hello?
phenomenon or a random experiment involves two steps. First step, we describe the possible outcomes of the phenomenon or experiment of interest. Second step, we describe our beliefs about the likelihood of the different possible outcomes by specifying a probability law. Here we start by just talking about the first step, namely the description of the possible outcomes of the experiment.
Okay. Sample space. 2 steps. Describe possible outcomes. Describe beliefs about likelihood of outcomes.
So we carry out an experiment. For example, we flip a coin, or maybe we flip 5 coins simultaneously, or maybe we roll a die. Whatever that experiment is, It has a number of possible outcomes, and we start by making a list of the possible outcomes, or a better word instead of the word list is to use the word set, which has a more formal mathematical meaning. So we create a set that we usually denote by capital omega. That set is called the sample space and is the set of all possible outcomes of our experiment. The elements of that set should have certain properties. Namely, the elements should be mutually exclusive and collectively exhaustive. What does that mean? Mutually exclusive means that if at the end of the experiment I tell you that this outcome happened, then it should not be possible that this outcome also happened. At the end of the experiment, there can only be one of the outcomes that has happened. Being collectively exhaustive means something else, that together all these elements of the set exhaust all the possibilities. So no matter what, at the end you will be able to point to one of the outcomes and say that's the one that occurred. To summarize, this set should be such that at the end of the experiment you should be always able to point to one and exactly one of the possible outcomes and say that this is the outcome that occurred. Physically
Okay.
different outcomes should be distinguished in the sample space and correspond to distinct points. But when we say physically different outcomes, what do we mean? We really mean different in all relevant aspects, but perhaps not different in irrelevant aspects. Let's make more precise what I mean by that by looking at a very simple and maybe silly example, which is the following. Suppose that you flip a coin and you see whether it resulted in heads or tails. So you have a perfectly legitimate sample space for this experiment, which consists of just 2 points, heads and tails. Together, these two outcomes exhaust all possibilities, and the two outcomes are mutually exclusive. So this is a very legitimate sample space for this experiment. Now suppose that while you were flipping the coin, you also looked outside the window to check the weather. And then you could say that my sample space is really heads and it's raining. Another possible outcome is heads and no rain. Another possible outcome is tails and it's raining. And finally, another possible outcome is tails and no rain. This set, consisting of 4 elements, is also a perfectly legitimate sample space for the experiment of flipping a coin. The elements of this sample space are mutually exclusive and collectively exhausted. Exactly one of these outcomes is going to be true or will have materialized at the end of the experiment. So which sample space is the correct one? This sample space, the second one, involves some irrelevant details, so the preferred sample space for describing the flipping of a coin, the preferred sample space is the simpler one, the first one, which is sort of at the right granularity given what we're interested in. But ultimately, the question of which one is the right sample space depends on what kind of questions you want to answer. For example, if you have a theory that the weather affects the behavior of coins, then in order to play with that theory or maybe check it out and so on, then in such a case you might want to work with a second sample space. This is a common feature in all of science. Whenever you put together a model, you need to decide how detailed you want your model to be, and the right level of detail is the one that captures those aspects that are relevant and of interest to you.
Interesting. Okay. So, oops. Okay. So, mean, that basically covers what the notes already say, so I wish there was a way to just go right into the next one. I'm gonna just open this puppy up. Oh look, some examples. I'm just gonna...
Let us now look at some examples of sample spaces. Sample spaces are sets, and the set can be discrete, finite, infinite, continuous, and so on. Let us start with a simpler case in which we have a sample space that is discrete and finite. The particular experiment we will be looking at is the following. We take a very special die, a tetrahedral die, so it's a die that has 4 faces, numbered from 1 up to 4. We roll it once, and then we roll it twice. We're not dealing here with 2 probabilistic experiments, we're dealing with a single probabilistic experiment that involves 2 rolls of the die within that experiment. What is the sample space of that experiment? Well, one possible representation is the following. We take note of the result of the first roll, and then we take note of the result of the second roll, and this gives us a pair of numbers. Each one of the possible pairs of numbers corresponds to one of the little squares in this diagram. For example, if the first roll is 1 and the second is also 1, then this particular outcome has occurred. If the first roll is a 2 and the second is a 3, then this particular outcome occurs. If the first roll is a 3 and then the next one is a 2, then this particular outcome occurs. Notice that these two outcomes are pretty closely related. In both cases we observe a 2 and we observe a 3, but we distinguish those two outcomes because in those two outcomes the 2 and the 3 happen in different order. And the order in which they appear may be a detail which is of interest to us, and so we make this distinction in the sample space. So we keep the 3-2 and the 2-3 as separate outcomes. Now this is a case of a model in which the probabilistic experiment can be described in phases or stages. We could think about rolling the die once and then going ahead with the second roll. So we have 2 stages. A very useful way of describing the sample space of experiments. Whenever we have an experiment with several stages, either real stages or imagined stages. So a very useful way of describing it is by providing a sequential description in terms of a tree. So a diagram of this kind, we call it a tree. You can think of this as the root of the tree from which you start, and the end points of the tree, we usually call them the leaves. So the experiment starts, we carry out the first phase, which in this case is the first roll, and we see what happens. So maybe we get a 2 in the first roll. And then we take note of what happened in the second roll, and maybe the result was a 3. So we follow this branch here, and we end up at this particular leaf, which is the leaf associated with the outcome 2, 3. Notice that in this tree we once more have a distinction. The outcome 2 followed by a 3 is different from the outcome 3 followed by a 2, which would correspond to this particular place in the diagram. In both cases, we have 16 possible outcomes. 4 times 4 makes 16, and similarly, if you count here, the number of leaves is equal to 16. The previous example involved a sample space that was discrete and finite. There were only 16 possible outcomes. But sample spaces can also be infinite, and they could also be continuous sets. Here's an example of an experiment that involves a continuous sample space. So we have a rectangular target, which is the unit square, and you throw a dart on that target, and suppose that you are so skilled that no matter what, when you throw the dart, it always falls inside the target. Once the dart hits the target, you record the coordinates x and y of the particular point that resulted from your dart throw. And we record x and y with infinite precision, so x and y are real numbers. So in this experiment, the sample space is just the set of xy pairs that lie between 0 and 1.
Okay. Oh boy, probability axioms. We're probably going to watch this one twice.
We have so far discussed the first step involved in the construction of a probabilistic model, namely the construction of a sample space, which is a description of the possible outcomes of a probabilistic experiment. We now come to the second and much more interesting part. We need to specify which outcomes are more likely to occur and which ones are less likely to occur, and so on. And we will do that by assigning probabilities to the different outcomes. However, as we try to do this assignment, we run into some kind of difficulty, which is the following. Remember the previous experiment involving a continuous sample space from which was the unit square and in which we throw a dart at random and record the point that occurred? In this experiment, what do you think is the probability of a particular point? Let's say, what is the probability that my dart hits exactly the center of this square? Well, this probability would be essentially zero. Hitting the center exactly with infinite precision should be zero. And so it's natural that in such a continuous model, any individual point should have a zero probability. For this reason, instead of assigning probabilities to individual points, we will instead assign probabilities to whole sets, that is, to subsets of the sample space. So,
Event. A subset of the sample space. Probability is assigned to events. A subset of this. So it's not an individual event because that probability would be zero. It's a set of possible events. But if. Here's what I don't get. If the probability would essentially be zero, why would it be the case that sets of events that are all zero would be anything more than zero? Like, how do we get there? I hope he gets to that point because that doesn't make any sense to me so far, but it must be the case. And so I guess they're saying zero because in a continuous space, absolute precision basically has an infinite chance of happening. That is to say, 1 over infinity, which I guess basically amounts to zero, but that's obviously not what happens. So let's see where we go from here.
here we have our sample space, which is some abstract set omega. Here's a subset of the sample space, call it capital A.
Got it.
We're going to assign a probability to that subset A, which we're going to denote with this notation, which we read as the probability of set A. So probabilities will be assigned to subsets, and this will not cause us difficulties in the continuous case, because even though individual points would have zero probability, if you ask me what are the odds that my dart falls in the upper half, let's say, of this diagram, then that should be a reasonable positive number. So even though individual outcomes may have zero probabilities, sets of outcomes in general would be expected to have positive probabilities. So coming back, we're going to assign probabilities to the various subsets of the sample space. And here comes a piece of terminology.
Okay, yeah, like, obviously that's the case. But, yeah, it's just hard to get there, you know? Like, Like, obviously, you're going to have more of a. If you break things out into larger chunks of stuff, it's going to make more sense that you're going to have a higher probability of hitting half the square as opposed to an individual point within that square in a continuous thing. But it still doesn't. It's not intuitively obvious why that would be the case. Like, maybe. I mean, I guess it's just that the chance of any individual spot in a continuous space would be so marginal, such as to basically be infinite. And I think that probably in order to get more precise, maybe you need more math than what they're getting into here. They're basically saying in essence it's zero, but it's not actually zero, but we'll just think about it in terms of the larger sets. Fine, I'll take it. But there is something a little unsatisfying about that, not gonna lie.
Technology that a subset of the sample space is called an event. Why is it called an event? Because once we carry out the experiment and we observe the outcome of the experiment, either this outcome is inside the set A, and in that case we say that event A has occurred, or the outcome falls outside the set A, in which case we say that event A did not occur. Now we want to move on and describe certain rules, the rules of the game in probabilistic models, which are basically the rules that these probabilities should satisfy. They shouldn't be completely arbitrary. First, by convention, probabilities are always given in a range between 0 and 1. Intuitively, 0 probability means that we believe that something practically cannot happen, and probability of 1 means that we're practically certain that, that an event of interest is going to happen. So we want to specify rules of this kind for probabilities. These rules that any probabilistic model should satisfy are called the axioms of probability theory. And our first axiom is a non-negativity axiom. Namely, probabilities will always be non-negative numbers. It's a reasonable rule. The second
Okay. So here are the axioms. Axioms. Non-negativity. P of A is less than or greater than or equal to 0. So not negative. 2. Normalization. P of some set omega is equal to 1. I think I understand that idea.
second rule is that if the subset that we're looking at is actually not a subset, but is the entire sample space omega, the probability of it should always be equal to 1. What does that mean? We know that the outcome is going to be an element of the sample space. This is the definition of the sample space. So we have absolute certainty that our outcome is going to be in omega, or in different language, we have absolute certainty that event omega is going to occur.
Okay. Which means this means that there is absolute certainty that within the set the event will occur.
And we capture this certainty by saying that the probability of event omega is equal to 1. These two axioms are pretty simple and very intuitive. The more interesting axiom is the next one that says something a little more complicated. Before we discuss that particular axiom, a quick reminder about set theoretic notation. If we have two sets, let's say a set A and another set another set B, we use the notation, we use this particular notation, which we read as A intersection B, to refer to the collection of elements that belong to both A and B. So in this picture, the intersection of A and B is this shaded.
I know it's called intersection. I'm probably just going to call these and or. And or.
Set. We use this notation, which we read as A union B, to refer to the set of elements that belong to A, or to B, or to both. So in terms of this picture, the union of the two sets would be this blue set. After this reminder about set theoretic notation, now let us look at the form of the third axiom.
Okay. So I want to look at this real quick. So finite additivity to be strengthened later, I think is what he says, but I'm just copying directly. If I'm going to just use logical notation, A and B and B equals 0, then the probability of A what do we use for or? Is it the line? Or B we'll just do that. B equals 0, then A or B equals the probability of A plus the probability of B, some event B. So if A and B equals 0, then the probability A or B, or A union B, equals the probability of A plus the probability of set B.
What does it say? If we have two sets, two events, two subsets of the sample space, which are disjoint. So here's our sample space, and here are the two sets that are disjoint. In mathematical terms, two sets being disjoint means that their intersection has no elements, so their intersection is the empty set, and we use this symbol here to denote the empty set.
Empty set. Okay.
So if the intersection of two sets is empty, then the probability that the outcome of the experiment falls in the union of A and B, that is, the probability that the outcome is here or there, is equal to the sum of the probabilities of these two sets.
That makes sense.
This
That
is
makes
called
total
the
sense.
additivity axiom. So it says that we can add probabilities of different sets when those two sets are disjoint. In some sense,
Yeah, I mean, this makes sense. Like, if they were intersected, then you would have to subtract the overlap in order to get the total probability, because the overlap would be accounted for twice. So you would need to subtract, the overlap of at least one of the sets, and then add up the difference, that is what wasn't overlapping, to get the probability. But if neither of them overlap, then it would, yeah, that makes sense.
we can think of probability as being 1 pound of some substance which is spread over our sample space, and the probability of A is how much of that substance is sitting on top of a set A. So what this axiom is saying is that the total amount of that substance sitting on top of A and B is how much is sitting on top of A plus how much is sitting on top of B. And that is the case whenever the sets A and B are disjoint from each other. The additivity axiom needs to be refined a bit. We will talk about that a little later. Other than this refinement, these three axioms are the only requirements in order to have a legitimate probability model. At this point you may ask, shouldn't there be more requirements? Shouldn't we, for example, say that probabilities cannot be greater than 1? Yes and no. We do not want probabilities to be larger than 1, but we do not need to say it. As we will see in the next segment, such a requirement follows from what we have already said, and the same is true for several other natural properties of probabilities.
I assume that has something to do with the fact that every number equals 1 of itself, so 2 over 2 is 1, so you can normalize any whole number to be 1 and just think about it in terms of that 1 would be how I think that would go. But I mean, listen, my math is garbage, so as we learn more about this, you know, it'll maybe I'm missing something. I look forward to seeing what I'm missing. I think I'm probably gonna get through most of this. I think, yeah, that was cool. That was cool. Let's keep crushing it. All right.
The probability axioms are the basic rules of probability theory, and they are surprisingly few, but they imply many interesting properties that we will now explore. First, we will see that what you might think of as missing axioms are actually implied by the axioms already in place. For example, we have an axiom that probabilities are non-negative. We will show that probabilities are also less than or equal to 1. We have another axiom that says that the probability of the entire sample space is 1. We will show a counterpart that the probability of the empty set is equal to 0. This makes perfect sense. The empty set has no elements, so it is impossible. There is 0 probability that the outcome of the experiment would lie in the empty set. We also have another intuitive property. The probability that an event happens plus the probability that the event does not happen exhaust all possibilities, and these two probabilities together should add to 1. For instance, if the probability of heads is 0.6, then the probability of tails should be 0.4. Finally, we can generalize the additivity axiom, which was originally given.
Is this the? I think there's a connection there between the probability of an event happening and the probability that it doesn't happening equals 1. I think that's connected to the idea of the principle of non-contradiction, right? I think that follows, right? Because so the principle of non-contradiction states that the principle of non-contradiction is this idea that two mutually exclusive things can't exist at the same time, because if they did, then from that you could basically prove that anything can happen. It has to be either one or the other, and that's as good as I can describe it right now. I should probably go and make that a lot more intuitive to myself, but look it up, principle of non-contradiction, and I will as well, and we'll try to grok it more, right? We need to master this, conquer it, rule over knowledge like we are gods. All right, keep going.
For the case of two disjoint events to the case where we're dealing with the union of several disjoint events. By disjoint here we mean that the intersection of any two of these events is the empty set. We will prove this for the case of three events, and then the argument generalizes for the case where we're taking the union of k disjoint events where k is any finite number. So the intuition of this result is the same as for the case of two events, but we will derive it formally, and we will also use it to come up with a way of calculating the probability of a finite set by simply adding the probabilities of its individual elements. All of these statements that we just presented are intuitive, and you do not really need to be convinced about their validity. Nevertheless, it is instructive to see how these statements follow from the axioms that we have put in place. So we will now present the arguments based only on the three axioms that we have available. And in order to be able to refer to these axioms, let us give them some names, call them axioms A, B, and C. We start as follows. Let us look at a sample space and a subset of that sample space, call it A, and consider the complement of that subset. The complement is the set of all elements that do not belong to the set A. So a set together with its complement make up everything, which is the entire sample space. On the other hand, if an element belongs to a set A, it does not belong to its complement, so the intersection of a set with its complement is the empty set. Now we argue as follows. We have that the probability of the entire sample space is equal to 1. This is true by our second axiom. Now the sample space, as we just discussed, can be written as the union of an event and the complement of that event. This is just a set theoretic relation. And next, since a set and its complement are disjoint, this means that we can apply the additivity axiom and write this probability as the sum of the probability of event A with the probability of the complement of A. This is one of the relations that we had claimed and which we have now established. Based on this relation, we can also write that the probability of an event A is equal to 1 minus the probability of the complement of that event.
Yeah.
And because by the non-negativity axiom, this quantity here is non-negative, 1 minus something non-negative is less than or equal to 1. We're using here the non-negativity axiom, and we have established another property, namely that probabilities are always less than or equal to 1. Finally, let us note that 1 is the probability always of a set plus the probability of a complement of that set. And let us use this property for the case where the set of interest is the entire sample space. Now, the probability of the entire sample space is itself equal to 1. And what is the complement of the entire sample space? The complement
0.
of the entire sample space consists of all elements that do not belong to the sample space. But since the sample space is supposed to contain all possible elements, its complement is just the empty set.
Yeah.
And from this relation, we get the implication that the probability of the empty set is equal to 0. This establishes yet one more of the properties that we had just claimed a little earlier.
That makes sense.
We finally come to the proof of the generalization of our additivity axiom from the case of two disjoint events to the case of three disjoint events. So we have our sample space, and within that sample space we have three events, three subsets, and these subsets are disjoint in the sense that any two of those subsets have no elements in common. And we're interested in the probability of the union of A, B, and C. How do we make progress? We have an additivity axiom in our hands which applies to the case of the union of two disjoint sets. Here we have three of them. But we can do the following trick. We can think of the union of A, B, and C as consisting of the union of this blue set with that green set. Formally, what we're doing is that we're expressing the union of these three sets as follows. We form one set by taking the union of A with B, and we have the other set C, and the overall union can be thought of as the union of these two sets. Now, since the three sets are disjoint, this implies that the blue set is disjoint from the green set, and so we can use the additivity axiom here to write this probability as the probability of A union B plus the probability of C. And now we can use the additivity axiom once more, since the sets A and B are disjoint, to write the first term as probability of A plus probability of B. We carry over the last term, and we have the relation that we wanted to prove. This is the proof for the case of three events. You should be able to follow this line of proof to write an argument for the case of four events and so on, and you might want to continue by induction, and eventually you should be able to prove that if the sets A1 up to AK are disjoint, then the probability of the union of those sets is going to be equal to the sum of their individual probabilities. So this is the generalization to the case where we're dealing with the union of finitely many disjoint events. A very useful application of this comes in the case where we want to calculate the probability of a finite set. So here we have a sample space.
Okay.
And within that sample space, we have some particular elements, S1, S2, up to Sk, k of them, and these elements together form a finite set.
Sure.
What can we say about the probability of this finite set? The idea is to take this finite set that consists of k elements and think of it as the union of several little sets that contain one element each.
It's like decomposing.
So set theoretically, what we're doing is that we're taking this set with k elements and we write it as the union of a set that contains just S1, a set that contains just the second element S2, and so on, up to the kth element.
Okay.
We're assuming, of course, that these elements are all different from each other. So in that case, these sets, these single element sets, are all disjoint. So using the additivity property for a union of k disjoint sets, we can write this as the sum of the probabilities of the different single element sets. At this point, it is usual to start abusing, or rather simplifying, notation a little bit. Probabilities are assigned to sets, so here we're talking about the probability of a set that contains a single element, but intuitively we can also talk as just the probability of that particular element and use this simpler notation. So when using this simpler notation, we will be talking about the probabilities of individual elements, although in terms of formal mathematics, what we really mean is the probability of this event that's comprised only of a particular element, S1, and so on.
Okay. I think I followed most of that. Basically, you sort of combine different events that are probable to happen as long as they are unions with no intersecting parts. You can basically split up a sample space into an infinite number of single events and calculate the probability of that through assessing the complement of the thing. I mean, I'm not saying it quite right, but we're just easing in here. This is just the beginning, and we're gonna keep plugging along. Let's see, that was simple properties of probabilities. We're gonna look at more properties. I think we can get through this whole thing. I think we can do it. We're at, what, almost an hour? Yeah. I'd like to get through most of it.
We will now continue and derive some additional properties of probability laws, which are again consequences of the axioms that we have introduced. The first property is the following. If we have two sets, and one set is smaller than the other, so we have a picture as follows. We have our sample space, and we have a certain set A, and then we have a certain set B, which is even bigger. So the set B is the bigger blue set.
Got it.
So if B is a set which is larger than A, then naturally the probability that the outcome falls inside B should be at least as big as the probability that the outcome falls inside A. How do we prove this formally? The set B can be expressed as a union of two pieces. One piece is the set A itself.
Okay.
The second piece is whatever elements of B there are that do not belong in A.
But also
What are
don't
these
belong in the
elements?
rest.
They are elements that belong to B and they do not belong to A, which means that they belong to the complement of A. So we have expressed the set B as the union of two pieces. Now, this piece is A. This piece here is outside A. So these two pieces are disjoint, and so we can apply the additivity axiom and write that the probability of B is equal to the probability of A plus the probability of the other set. And since probabilities are non-negative, this expression here is at least as large as the probability of A, and this concludes the proof of the property that we wanted to show. Indeed, the probability of A is less than or equal to the probability of B. The next property we will show is the following. It allows us to write the probability of the union of two sets for the case now where the two sets are not necessarily disjoint. So the picture is as follows. We have our two sets, A and B. These sets are not necessarily disjoint. And we want to say something about the probability of the union of A and B. Okay. Now, the union of A and B consists of three pieces. One piece is this one here, and that piece consists of those elements of A that do not belong to B, so they belong to B complement. This set has a certain probability, let's call it little a, and indicate it on this diagram. So A is the probability of this piece. Another piece is this one here, which is the intersection of A and B. It has a certain probability that we denote by little b. This is the probability of A intersection B. And finally, there's another piece.
Okay. The thing that I'm having a little trouble grasping right now is I thought the complement was primarily the stuff that wasn't included in B, including the rest of the sample space. Uh-oh. I'm gonna have to get like a better camera or something, cause my camera just can't handle being on this long. get it. It's not meant to do that, but you know. Okay. So, yeah, I mean, I thought that the complement of B would include everything that wasn't B, including what would be A, but also like the rest of the set, no? So, that's where I'm getting a little lost. Isn't like the complement of B like oh, come on, cat. Don't chew on wires. Hmm.
which is out here. And that piece has a certain probability C. It's the probability of that set. And what is that set? That set is the following. It's that part of B that consists of elements that do not belong in A. So it's B intersection with the complement of A. Now let's...
Maybe they're just, in this case, it just refers, I mean, it either just involves the union that, or the connection between the two as an entire unit and is disregarding the total set or omega, or it's, or I'm missing something else, but that seems to be how they're using it, is just this overall unit thing of both of these elements we're considering.
express the two sides of this equality here in terms of little a, little b, and little c, and see whether we get the same thing. So the probability of A union B. A union B consists of these three pieces that have probabilities a, little b, and little c, respectively. And by the additivity axiom, the probability of the union of A and B is the sum of the probabilities of these three pieces. Let's look now at the right-hand side of that equation and see whether we get the same thing. The probability of A plus the probability of B minus the probability of A intersection B is equal to the following. A consists of two pieces that have probabilities little a and little b. The set B consists of two pieces that have probabilities little b and little c. And then we subtract the probability of the intersection, which is b, and we notice that we can cancel here one b with another b, and what we are left with is a plus b plus c. So this checks, and indeed we have this equality here. We have verified that it is true. One particular consequence of the equality that we derived is the following. Since this term here is always non-negative, this means that the probability of A union B is always less than or equal to the probability of A plus the probability of B. This inequality here is quite useful whenever we want to argue that a certain probability is smaller than something, and it has a name. It's called the union bound. We finally consider one last consequence of our axioms, and namely we're going to derive an expression, a way of calculating the probability of a union of three sets, not necessarily disjoint. So we have our sample space, and within the sample space there are three sets. Set A, set B, and set C. We're going to use a set-theoretic relation. We're going to express the union of these three sets as pieces. One piece is the set A itself.
Oh, darn it. All I did was scream.
The second piece is going to be that part of B which is outside A. So this is the intersection of B with the complement of A. The third piece is going to be whatever is left in order to form the union of the three sets. What is left is that part of C that does not belong to A and that does not belong into B. So that part is C intersection with A complement and B complement. Now, this set here, of course, is the same as that set, because intersection of two sets is the same no matter in which order we take the two sets. And similarly, the set that we have here is the same one that appears in that expression. Now, we notice that these three pieces, the red, the blue, and the green, are disjoint from each other. So, by the additivity axiom, the probability of this union here is going to be the sum of the probabilities of the three pieces, and that's exactly the expression that we have up here.
Okay, I think I'm tracking that. Notice how I'm not taking notes right now. 4 more videos. I'm trying to decide whether I want to just put this on hold for the moment. I think I've put in some solid work today on this particular subject. Okay, so originally the plan was to do statistics. This is meant to be a supplement so I can get into the more complex statistical class, the fundamentals of statistics or applications of statistics class. This seems definitely manageable right now. So here we have some lecture 1, some mathematical background stuff. I'm probably going to check into that. See, we're going to go over some Bayesian stuff, independence, counting, discrete random variables, 2, 3, continuous random variables, derived distribution, sum, and independent. This is all really, really good stuff. Let's see what else we got here. If I go to the class homepage, oh, it just keeps going, huh? This is a solid class. What I'm not seeing is like homework. I see lecture notes, I see videos, and I see slides. We got a textbook. Okay. Okay, I'm gonna call it there. I've got some other things to do. This was a solid beginning place. I think Okay, so I feel like my videos, if I were to make some videos on this stuff, they're probably going to be garbage until I get a better grasp of what's going on such that I can teach it. So I'm going to keep working through this stuff and studying. I might try to set up like some worked examples so I can try and grasp this a bit more. Because right now, like I was trying to think about doing some videos earlier, but I think my fundamental understanding is just a little too horrible at the moment for me to produce content on it. I need to develop some expertise to be able to talk about it. So that's sort of the process we're in now. Like this whole shtick, we're gonna record it, we're gonna develop our expertise, and then I'm gonna probably try to produce some videos to talk about what it is I've been learning in terms of probability and statistics and how I might want to apply it in the future. I appreciate you bearing with me. If you are enjoying any of this content, please feel free to go to patreon.com/mindofmeaning. I want to find some time to and find some willing victims who might want to do some street epistemology, and maybe I can start off by being the victim and then reverse it, and maybe even I can pull some people on to do some Nolanda debate type stuff, and we can play with that as well. I'm just sort of, I'm just messing around. I don't know where we're gonna end up with this, but we'll see what happens. Should be fun. Should be interesting. And until next time, thank you for bearing with me. And you have a fantastic day. All right. Until next time. Adios.